Good day, everyone. I'm glad to be part of this conference, and I want to present a paper on differential scanning calorimetry (DSC). This DSC is a thermoanalytical technique in which the relative distance in the amount of heat needed to raise the temperature of a substance and the reference material, which is usually inert material, are measured as a function of temperature. And we have the formula here where the delta H is the enthalpy of transition, K is a constant, and A is area under the curve. Now this curve is as a result of what we get from the output of a DSC. The output of a DSC always produces a thermogram, a plot of heat flux against either time or temperature. So the area under the curve multiplied by this constant gives us the enthalpy. Now we have DSC as applied to the heat capacity of a substance. Now how do we measure the heat capacity of a substance using DSC? In order to obtain reliable results, three measurements are usually carried out: the sample, the pan, which is the baseline in our plot, and a standard or reference. We can actually see that from the plot, the pan is heated alone, and then the pan plus the sample is heated. The formula we have below is an expression to derive the heat capacity, where we have dH all over dt is equal to constant multiplied by Cp, which is our heat capacity at constant pressure. It is also important to note that the standard sample should have a well-defined heat capacity over a range of temperature to be scanned. Now these are the kind of plots we get after our DSC, which we are going to discuss earlier and later what these plots, how they can be used to describe and to get the temperature and the enthalpy of the substance. The applications of DSC. We have listed various applications of the DSC, and we are going to discuss the vital ones in subsequent slides. This is the thermograph. Since the main application of this DSC is in studying phase transitions, we are now going to explain these phase transitions. Now we have a general plot. From this plot, we can see that the TG, which is the glass transition, the TC, which is the crystalline temperature, and the Tm, melting temperature, are all indicated in this plot. And we want to use this plot to explain in general how a DSC is used to explain both the glass temperature and the TC and then Tm. For a sample undergoing a change in heat capacity, we talk about the glass transition, which is moreover subtle kind of phase change. Here we are not talking about the formal phase change, we are talking about a change in heat capacity. It occurs as the temperature of the amorphous solid is increased. Now when this temperature is increased, a stage is switched where the amorphous solid will become less viscous. At some point, the molecules may obtain enough freedom, if still heated above this viscous temperature. They will obtain enough freedom of motion to spontaneously arrange themselves into a crystalline form, which is this TC we are seeing in the plot. And then when further heat is added, our Tm, which is the melting temperature, is reached, which is an endothermic process since heat is added to get to this temperature. Now we want to talk about the percentage crystallinity of polymers, which is also where we can apply this DSC. DSC provides a rapid method for determining polymer crystallinity based on the heat required to melt the polymer. This is achieved by the measurement of enthalpy of fusion and its normalization. Heat of melting is obtained by taking area under the endothermic peak, which we have already shown in the plots, and we can still see them in this plots marked blue, endothermic peak, where it absorbs heat. Now we'll take the area under this endothermic peak, and the heat of cold crystallization is obtained by taking the area under the exothermic peak. Then the formula to determine the percentage crystallinity of polymer is shown. These are the components of the DSC. We have the holder, which contains both the reference and the sample. We have already identified the sample and the reference here as S and R respectively, so they are contained in this holder. And then we have the furnace to supply the heat. The sensors are also there to regulate this heat. We want to talk about now the advantages and disadvantages, which are the pros and cons of DSC. We've said here that DSC can be used at very high temperature. A DSC is highly sensitive. Characteristics, transitions, or reaction temperature can be determined. Results are obtained within a short period. This is actually why it has become one of the frequently used methods in determining the enthalpy of a substance. This is why, because you obtain your results within a short period. Then the DSC measurement uses very small sample. You don't actually need a very big sample to obtain a very good result. A small sample is enough for that. Now we have the disadvantages. We know in reality that whatsoever has an advantage also has disadvantages attached to it. Now the disadvantages of using this DSC is that it is actually unsuitable for composite materials. In other words, you cannot obtain a reliable result for any composite materials with the method DSC. The DSC does not detect gas generation. Difficulties in avoiding evaporation while preparing samples of volatile solvents. That is the last and not the least of the disadvantages of the DSC. And we go to the next slide. We want to review literatures, how people have used this method DSC in their various research works. Strasdart 2013 carried out a research work on the characterization of lipid nanoparticles incorporated into calcium arganate bits. Now he did this, the goal of his experiment, of his research work rather, is stated here. But we are not actually interested in the whole work. We want to know the role the DSC played. This DSC was used in this work to examine the stability of the enclosed nanoparticles and the lipid content in the microbead. Now we are going straight to the result done with this DSC in the characterization process. Now we have two plots here. From the first plot, which is labeled DSC curve of a small sized times 3 nano emulsion during heating, cooling, and reheating. Now from this curve we are seeing first heating and second heating. The samples were first heated from 20 degrees, which the first heating line has shown, from 20 degrees to 70 degrees, and held for 5 minutes and then cooled to -5 degrees. Finally, he heated them again to 70 degrees with a rate of 10 degrees C. Now for the data interpretation, the curves here are normalized with respect to sample weight, and the results he got from the research work is stated below. From the result, it is stated that the DSC measurement revealed the characteristic melting behavior of small size trimethylene nanoparticles. Information about the trimethylene concentration was deduced from DSC thermographs from the integral of the crystallization and melting signals. The lipid nanoparticles are stable even in the presence of significantly high concentration of calcium chloride. That is what Nsukka did, how he used this DSC in his work 2013. Now we are going to talk about another work, and this is Yongcho 2019. He used this DSC in the characterization of electrospun PVA, which is polyvinyl alcohol and polyvinyl alcohol cellulose nanocrystal composite nanofibers. And we have stated what he intended in getting at the end of his research work. But then, just like we did in the previous slide, we are not interested in everything that happened in the work. We just want to go ahead to illustrate the usefulness of this DSC in carrying out the work. First of all, he had a goal to observe the electrospinning enhancement of the thermal conductivity of pure polyvinyl alcohol PVA and its composite with cellulose nanocrystal. Now, what was the contribution of this DSC in this experiment? Let's discuss further. Now, after the DSC was conducted, it gave a curve, which we have seen. We got two curves, A and B. Now, from curve A, we've seen that the endothermic peaks exhibited a shift of melting temperature from 226 degrees to 220 with an increase in CFC for up to 10 degrees, 10% of our CNC. From curve B, the DSC characterization shows that the percentage crystallinity of bulk PVA was lower than that of neat PVA nanofibers. Now, after this research work, he concluded that the thermal conductivity of polyvinyl alcohols through CNC nanofibers was enhanced by reinforcement of their backbone rigidity, while that of the neat polyvinyl alcohol nanofibers was attributed to the increase in their crystallinity that occurred during electrospinning. This was actually effective by the contribution of the DSC in the research work. That is what Yongcho did 2019. Now we have another work from Guerrero 2008. He did a research work which was centered on the characterization of smart copolymeric nanohydrogels, and in the aim of this work was to obtain the glass temperature of novel smart copolymeric nanohydrogels. What was the contribution of the DSC to this? From the DSC plot, or curve rather, the glass temperature TG was determined based on the midpoint criterion. This is the calorimetry curve for nanohydrogel. The glass temperature was assigned by the midpoint criterion, and these are the results he also got. So this is actually showing us that this DSC is effective in characterization works basically. Ding 2002 carried out a research work on characterization of nanoscale PVA fiber aggregate through electrospinning. The aim of his research work was to improve the anti-water solubility and mechanical properties of polyvinyl alcohol through electrospinning and cross-linking with glyoxal. After the use of the DSC method, he got these plots. Now we have, in this plot, we have from A to G. The plot in the DSC thermograms over a temperature range of from 30 degrees, which we can see from the plot. We have a curve from 30 degrees to 250 degrees Celsius. From line A and B, it is observed that after electrospinning, the melting temperature increased because of the molecular orientation in the fiber aggregate was higher than that of the PVA powder. From line B to line G, we observe a rapid decrease in the enthalpy of fusion and melting temperature, which suggests that the crystallinity and perfection of crystal structure were reduced with the degree of cross-linking. Increased. Again at G, the melting point disappeared when PVA fiber aggregates were cross-linked properly. Now our conclusion. The DSC technique finds wide application in thermal analysis of nanoscale materials, including perimetric, polymeric nanomaterials. Of course, we've reviewed several literatures and we came to conclusion that it is actually important in thermal analysis of nanoscale materials. These are the major limitations of DSC listed below. Thank you very much.